In this video, we'll go over some basic systems of equations problems, primarily two variable, and then we'll do one three variable system at the very end. Just quickly though, like you've all seen things like this probably on Facebook or something, maybe in like your third aunt twice removed posts it. But these are effectively what they boil down to are systems of equations problems. Like we could see here that these cups, these are all 10, right? Each cup is 10. Then we see, all right, a cup, which is 10 plus 2 burgers is 20. That means a burger must be 5, right? And then we say, okay, a burger, which is 5, plus 1, so and this is where they trick you always, right? There's 1 fries here, there's 2 fries here. So this is 5 plus 4 things has to equal 9. So each fry is 1. We know a burger is 5, and then we know the cup is 10, and nothing's weird, nothing's fishy about the cup or the burger. So order of operation tells us that this is 10. 1 times 10 is so 5 plus, so this should be 15, I think. Hopefully I'm right. But anyway, they're like this, and they get more complicated. Like this one has to do with the number of sides inside of these nested polygons like this. But in any case, these are systems of equations problems. They're just using abstract like shapes and objects to like, we're basically in our head assigning values to them, just like we do with variables. So this here is really the same thing as those pictures. This is just a two variable system of equations, linear, so there's no weird stuff going on. 7x minus 6y equals negative 11, and negative x plus 2y equals 21. Now we've already discussed in previous video that the fastest way, if you have Desmos or something available to you, to find a solution to a system of equations is to graph it and then find the intersection point, and that would be the xy point that satisfies, or it could be multiple xy points that satisfy a system, if they're not linear. But we're gonna assume that we don't have that kind of thing available and focus on the two different algebraic approaches that we have, and they are substitution and elimination. And in this one, I'm going to do substitution, and I don't really have a reason for it besides that this equation, the second one here, the bottom one, seems to be pretty ready for that. I can solve this really easily for x. I can rearrange it and say that x is equal to 2y minus 21. And then what I can do is plug that value for x back into my equation, my first equation. So if I plug in x equals 2y minus 21, basically what I'm going to have is 7 times what I just said x was, 2y minus 21, and then minus 6y equals negative 11. Then we just solve for y here. So we have to distribute this out. 7 times 2y is 14y, minus 7 times 21, that's 147, minus 6y equals negative 11. Then we have 14y minus 6y is 8y, and if we add 147 to both sides, we'll have 136. Divide both sides by 8, you'll find that y is equal to 17. Now if I have that y is equal to 17, I could take this y and plug it back into this equation where I already had solved for x. So now we'll say x is equal to 2 times 17, which is what we said y was, minus 21. So x is equal to 2 times 17, which is 34, minus 21, so x is 13. And now, because this is a line, these are two variable systems, and we're using x and y, we can assume that we'd want this answer written as an ordered pair x, y. And so that's what we're going to write it as. So x was 13 and y was 17. And that's how you do a problem like that with substitution. Let's look at one where maybe this next problem will do elimination. Okay, here's a problem, and this one has fractions in it, but that's no big deal. And what elimination is, and let's actually label each equation. Let's call the top one equation 1, the bottom one equation 2, is that we're going to multiply one of the equations by a number in order to try to get the same amount of the same coefficient in front of one of the variables as is in the other equation, and then we can just cancel them out. So what I want to do is I'm going to look at the coefficients of the y values and the x values and think, is there a number that I might be able to multiply equation 1 by in order to get the same value as one of these coefficients in equation 2? And to me right away, and this might not be the same for you, there's many ways to do this, is if I took equation 1 and multiplied it by negative 12, and then if I added that to equation 2, what's going to happen is I'll be able to cancel out the y values. So let's see what that looks like, right? If we take negative 12 times 2/3, that's going to be negative 8x plus, minus, if we take negative 12 times 1/2, we'll have negative 6y and then we'll have, and that equals 1/6 times negative 12 is just negative 2. So that's my new, like, we call this, actually, you call this like equation 3, right? This is like equation 3. Then I'm going to put equation 2 there, and I'm going to add the equations. So equation 2 was 4x plus 6y equals negative 1. And when we say we're going to just add these equations, really, we're just adding them. We're going to add the x's, add the y's, and then add the constants at the end. So we end up with negative 8x plus 4x is negative 4x. There's no y's, right? Plus 0y. And then negative 2 and negative 3 is, negative 2 and negative 1 is negative 3. And if we solve this for x, x would equal positive 3/4. So that's what x is equal to. And then it's just a matter of, as long as we did that right, we know that we got the right answer for x, it's just a matter of plugging this x equals 3/4 in to either of these two equations, because we know that this is the x value that satisfies both of the equations. So either one, if I plug x in, I'll get the y value that satisfies that equation. So let's just plug it into the bottom one, because in equation 2, because it's like whole numbers and we don't have to worry about weird multiplication. So it'd be 4 times 3/4. That's what x is equal to, plus 6y equals negative 1. So this would just be 3 plus 6y equals negative 1. 6y equals negative 4. Y would equal negative 2/3 after you solve for y. So then again, to write this answer in an ordered pair x, y, we would write x, what was x? 3/4, and then y was negative 2/3, and that's it. Okay, so the more interesting thing about systems of equations is that we can actually use them in some cases in the real world to solve problems. Now, generally speaking, in math class, the problems that you're given are not at all real world problems. Like this one maybe is if you were dealing with chemistry class or something, but the idea is the same. We can assign variables of things we don't know and see if we can work out a solution. So step 1 is to assign variables, and in this case we'll say that x is equal to the amount of a 4% solution that Chelsea has, and we'll say that y is equal to the amount of 12% solution that she has. Now together she needs to make a 9% solution. So what that tells me is I can write two systems of equations. I can say, let's write one for the amount of actual acid that needs to be added to this. So we have some amount, so we have 0.04 is the concentration of acid in the amount. So if we multiply 0.04 times x, that is the amount of pure acid in that component of this mixture. And then if we add that, if we add 0.12 y, right, 0.12 is 12%, that will give us the total amount of pure acid, which we know is 0.09 times 60. So that would be equation 1. And then equation 2 is just talking about the actual volume involved. So I could say that the volume of x plus the volume of y, or the amount of x plus the amount of y, is going to equal a total of 60 milliliters of solution. And so now all that's left is for me to solve this. And for me, what I see right away here is if I multiplied the top equation by 100, I would get rid of all the decimals. So let's do that. So if this was equation 1 and this was equation 2, I'll say equation 3 is just 100 times equation 2. So equation 3 is going to be 4x plus 12y equals 540. Okay, now all I need to do is do a system here, and I think substitution or elimination would be equally doable here, but I'm going to go with elimination. So I'm going to multiply here. I'm going to take equation 2 and I'm going to multiply it by negative 4 to get rid of the x values, and I'm going to then add that to equation 3. Okay, so if we do that, what we'll get negative 4 is negative 4x minus 4y equals, and then negative 4 times 60 is negative 240. And then we're going to add that equation 3 was 4x plus 12y equals 540. Okay, and then we're just going to add these. Okay, add them up. So add them up. Sorry. So when we do that, we will get that there are 0x, and then we'll have 4y and negative 4y and 12y is positive 8y, and then negative 240 plus 540 is 300, And then if we solve this for y, where y is equal to 308, which is the same thing as 37.5, 37.5. So we found that there's going to be 37.5 milliliters of the 12% solution. Now that all that's left is to find out how much of the other solution we have. And the easiest way to do that, we have a direct relationship between the volume of x and the volume of y here, and that's that the sum is 60. So to find what x would be, right, x is going to equal, so we just solve this equation here for x. So we subtract and we find that x is equal to 22.5 milliliters. So to answer this question, it's a little bit different because it's a word problem and all these variables are meant to talk about a specific thing. It would be, we would say, she needs to add whatever. We could just say there's 22.5 milliliters of 4% solution, and there's 37.5 milliliters of 12% solution. And then that would be our answer right there. So we don't have to, we don't write that as an ordered pair because in this case, x and y are not corresponding to coordinate points, or corresponding to volumes. Here's another one. In this case, I'm just going to try to do this one quickly. We're going to say x equals the number of student tickets sold, and then y is equal to the number of regular tickets sold. So what this is saying then, if I wrote a system here, it would be that $3 times the number of student tickets plus $5 times the number of regular tickets is equal to $10,000, and that combined there were a total of how many tickets sold? 3,000 tickets. So all I'd have to do here, I'm gonna add equation 1 to -3 times equation 2, and I'll do that. So that means it's 3x plus 5y equals 10,000, and then -3 times equation 2 would be -3x minus 3y equals 9,000, -9,000. If we add these, we'll find that 2y is equal to 1,000, which tells me that there were y is going to equal 500 regular tickets, right? Because we have 500 regular tickets, so this would be 500 regulars, and that means there's got to be 2,500 students, because together they had to add up to be 3,000. And this one's a little different. So an airplane goes 1,400 miles in 4 hours with a tailwind, so it's got two speeds pushing it, its own speed plus the wind. And then on the way back, it's got the same situation here. So if we called this speed W and then this speed was like the plane speed, call it like R, we have two situations. And so we just write two equations based on what's given to us in the problem here. And it says on the way there, so on the way there, it's basically rate. So we know rate times, distance equals rate times time, right? And so we know then that the rate, which in this case is the combination of R plus W on the way there, times the 4 hours, that's equal to the total distance of 1,400 miles. And then on the way back, what we can say is that the rate minus the wind, right? Because it's going slower, that took 5 hours and it went 1,400 also. So now all we have to do is solve for R and W, and it's actually easier than it looks, because if we divide both sides of this equation by 4 and divide both sides of this equation by 5, what we get is what is 1,400 divided by 4? Divided by, so it's 300, right? So R plus W is equal to 350, right? And then on this one, R minus W is equal to, divide this by 5, so there's 200, how come I can't do this in my head? 280, right? All right, so now all we have to do here is solve for R and W, and it's nice because there's already a positive W and positive R, so we just add these two equations together. We'll get that 2R is equal to 350 times 350 plus 280, which is 630, which means that R, the speed of the airplane itself, was 315 miles per hour. And then the wind, right, if the wind plus the speed of the airplane was 315, that means the wind was 45. No, it doesn't. It means it was 35 miles per hour. And so, we could write that. We could say the speed of the wind was 35 and the speed of the airplane was 315. All right, now this is a three-variable system of equations. We have three variables and three unknowns and three equations, which is fine. We'll be able to solve this. But the strategy is that we're going to take two of the equations, eliminate a variable, and then take another two of the equations, eliminate the same variable, and then it's basically a two-variable system. At that point, all we have to do is solve for those two variables, plug them both back into any of the three original equations, and then get our answer. So what I'm looking at here is I'm looking at equation 1 and 3. So I'm going to add equation 1 plus equation 3, and what that's going to do is get rid of the y's. So if I take negative 6x plus 5y plus 2z equals negative 11, and then I add 4x minus 5y plus 5z equals negative 4. If I add these, I'm just going to get negative 2x, no y's, that's the whole point, plus 7z equals negative 15. So we'll call this equation 4. Now what I want to do is take another two of the equations that are up in the original three, and I'm going to add them or do an elimination again to get rid of y. So easiest ones that I see are 2 and 3. So I'm going to take equation 2 and I'm going to multiply it by positive 5, and then I'm going to add that to equation 3. And so 5 times equation 2 gives me negative 10x plus 5y plus 20z equals negative 9 times was negative 45. And then equation 3 was my 4x minus 5y plus 5z equals negative 4. And so what we end up with when we add these is negative 6x plus 25z equals, and then it's negative 49. Okay, so here's this, we'll call this equation 5. And now what I want to do is look at equations 4 and 5 and see how can I add those together to get rid of either variable. I'm looking at x to get rid of, ideally. So what I'm going to do there is I'm going to take negative 3 times equation 4, and I'm going to add that to equation 5, and that's going to get rid of the x values. So we'll have negative 3 times equation 4 to give me 6x minus 21z equals positive 45, and then equation 5 was negative 6x plus 25z equals negative 49. And so if we add these, we'll have that 4z is equal to negative 4. So therefore, right, z is equal to negative 1. Now, that's mostly the entire problem, because at this point, either of these two equations that we have, either of these two equations just talk about two variables, and if we have one of them, we can find the other. So we can find x right away. Let's plug this right here back into equation 4. And when we do that, we'll find that it's negative 2x plus 7 times negative 1 is equal to negative 15. I apologize for the squiggly lines here. I'm not exactly sure what's going on. 2x minus 7 equals negative 15. So if we add 15 to both sides, add 7 to both sides, negative 2x will equal 8, negative 8. So x is 4. So we have x is 4, we have z is negative 1, and then the last thing we have to do is plug it back into one of my original equations. So let's plug it back into this one. We know negative 2 times 4, that's what x was, plus y, which we don't know, plus 4 times z, which was negative 1, that equals negative 9. So we have negative 8 plus y minus 4 equals negative 9. So that is negative 8 plus negative 4 is negative 12. So y minus 12 equals negative 9. Well, I really don't know what's going on with this pen I'm using right now. y minus 12 equals negative 9, so we add 12 to both sides, we find that y equals 3. Now we can write this as an ordered triple xyz, and we'll talk a little bit more about why this is. But if we write it as an ordered triple xyz, x was 4, y was 3, and z was negative 1, so we'd be done with that one.